So right off in the morning, we are going to get started with Mary Muller's talk. Mary Muller is a researcher at Ethereum Foundation, and you previously know her from UCL, where she worked with Sarah Michael-John and others there. And she is going to lead off this day with a talk on zero knowledge proofs, or more specifically, inner product arguments. So Mary, please take it away.
Thanks for the introduction. Hold on, I just need to share my screen and start my slides. Okay, can everyone see these okay?
Looks good.
Excellent. So today I'm planning to talk about inner product arguments, and these, if you're not already aware, are pretty much the key technique behind bulletproofs and similar protocols to that. I think in general, I've had quite a lot of people ask me, do you have a very nice intuition as to how these work, how the maths actually sort of comes out and provides a sound argument? And usually my answer to this is no, I don't. But what I was thinking I would do today is, rather than try to give you a sort of high level, this is how it works, I would give a very specific, very small example and walk through it in a lot of detail, in the hope that you can sort of get a feel for how they work, as opposed to an intuition. So it will be quite technical, and if you have pen and paper, or if you prefer to work on a computer or something like that available, then that would be quite helpful for this talk. Also, it would be good if you already know a little bit about discrete log problems and Schnorr signatures, because I don't really intend to go into those, but they will sort of be coming up throughout the talk. If you don't know these and you're watching this talk online, or you're planning to come back and watch it on YouTube earlier, then there are lots of great resources. In particular, Dan Binet and Victor Shoup did a graduate course where you can look up on these things, and I would strongly recommend giving that a look. And with Schnorr signatures, actually, the Wikipedia page does a pretty good job. So this is a list of inner product arguments that I'm aware of. There's plenty more, but these ones are all using the tricks which I will be talking about in this talk. So you'll see bulletproofs listed there. You'll also see a work which is the precursor to bulletproofs, and that's by some people at UCL. Then there is some work on how to actually get zero knowledge for these arguments, as well as how to extend these arguments to parent-based groups and different types of commitment schemes. And all these papers can be accessed for free on ePrint, as can many other cryptography papers. So I'm here going to just give a quick overview of what it means to be a zero knowledge argument. Actually, the stuff I'm going to be talking about in this slide is merely a sort of argument of knowledge, as opposed to something which is zero knowledge, but I think sort of calling it a zero knowledge argument, even though this is extremely untrue, gets across the point of sort of what we're trying to get at. So you have a computation, and what you're trying to do is you're trying to prove to a verifier that the output of this computation is correct. The verifier is not going to be able to compute these things for themselves, so it's something that you have to convince them of. And you need two properties. The most important is soundness. If the result is wrong, then the prover should not be able to convince the verifier. For some properties, you also require zero knowledge, and this means that the verifier should learn nothing about the inputs of the computation. And inner product arguments, as mentioned before, that can be extended to be zero knowledge, but just a baseline isn't. Soundness is typically the more difficult property to achieve, though, especially because for lots of the more modern arguments, we have very, very small proof sizes. So if you're wanting to achieve zero knowledge, then you just need to sort of throw some randomness in there, and you don't need to throw that much randomness in there because the argument sizes are very small. But equally, if you're sending only a very small amount of information, then the amount of information you're able to convey in order to convince someone that something is true is much less. So going to start off with a very simple inner product argument. We are going to be working in the discrete log setting. So we have a group and we assume that the discrete log is hard. It's hard to compute, well, given g to the power of x, it's hard to compute x. Now we're going to be given 3 group elements in G, and we want to prove knowledge of some exponent b such that b is equal to g to the power of b, where g is our generator, and c is equal to a to the power of b, where a is one of our inputs. And I'm calling this a one-dimensional multi-exponentiation problem, or just exponentiation problem here. So for this example, probably what you would do is use the, if you weren't worried about zero knowledge, is use the simplest solution you can imagine. The prover is just going to directly reveal B, and the verifier is going to check for themselves that B is equal to G to the power of B and C is equal to A to the power of B. So with that example, you really can't see what's going on. So I'm going to sort of go one dimension up and talk about the 2-dimensional case. So here we're assuming that you have 2 generators as opposed to 1, G1, G2. These should be independently generated. And now you're going to be given 2 group elements, A1 and A2, as opposed to just A. And you're going to be trying to prove knowledge of 2 field elements, B1 and B2, such that B is equal to G1 to the B1, G2 to the B2, and C is equal to A1 to the B1, A1 to the B2. It's our 2-dimensional problem. So the solution to this is going to be a 3-move solution. It's going to look quite Schnorr-like in nature. So we're going to have a prover. They're going to compute some message. They're going to send their message to a random oracle or a hash function. And in response, the hash function is going to give them some randomness back. Given the second piece of randomness, the prover is going to, well, the first piece of randomness, the prover is going to compute the second message. And then the proof that they're going to output is going to be these 2 messages, M1 and M2. Likewise, the verifier is going to act very similarly. It's going to receive M1 and M2 from the prover. It's going to send M1 to the hash function in order to receive the same randomness as the prover received, ideally. And from the first message and the randomness and the second message, they're going to decide whether or not they believe that the prover genuinely does know of some B1, B2, such that B and C satisfy this property. So specifically, the prover is going to send 4 group elements in the first message. And these group elements are going to be related to the generators and the exponents B1 and B2. So BL is going to be equal to G2 to the power of G1, B1. BR is going to be equal to G1 to the power of B2. CL is going to be equal to A2 to the power of B1, and CR is going to be equal to A1 to the power of B2. Given these messages, you're then going to compute the hash of them in order to get some randomness X. And this X, you now know, is going to be entirely independent from BL, BR, CL, CR, because we're in the random oracle model. And from this X, the prover is then going to compute their second message, which I'm calling BF here to stand for B final, but there's other notations you could use. And they're going to compute Bx to be equal to B1 plus B2 x to the minus 1. And then they're going to return their first message, BL, BR, CL, CR, BF to the verifier, and the second message, BF, to the verifier. The verifier is then going to first compute the randomness X, same as the prover did. And then they have two verification equations which they're going to need to check. They're going to need to check that BL to the power of x times B times BR to the power of x to the minus 1 is equal to G1, G2 to the power of x, all to the power of B final. And similarly for the CL, C, and CR, but with respect to our public inputs A. So I've run out of space, so I'm now going to squish up the information on this slide to give me more space, but the information next is going to be the same. So the first thing that you sort of need to observe here in order to check that, yes, the prover is actually demonstrating knowledge of B1, B2 that is satisfying the problem. So B equals G1 to the B1, G2 to the B2, and C equals A1 to the B1, A2 to the B2, is to just check correctness. Just check that if the prover behaves honestly and the verifier behaves honestly, then everything terminates correctly. And the general way you do this is you just expand out the equations. So if we just look at the first verification equation, so BL to the power of x, B, BR to the power of x to the minus 1 is, and we expand that out in terms of what we know BL to equal, what we know B to equal, and what we know BR to equal. Then first we're going to have that BL is equal to G2 to the power of B1. And in the verification equation, BL is taken to the power of x. So that gives you a term G2 to the power of B1x. Sorry, G2 to the power of B1x. In terms of B, you're not going to have to change anything. That's just G1 to the B1, G2 to the B2. And in terms of BR, that's G1 to the power of B2, x to the minus 1. And when you simplify those down, you can take all of the exponents in the G1 term together and all of the exponents in the G2 together, a term together, in order to have as compact a representation of what's going on there as possible. You then have the right-hand side of the equation. So G1 to G2 to the power of x, or to the power of BF, and you're going to be trying to check that that is genuinely equal to the same thing. And this time, you know BF, you know that's equal to B1 plus B2 x to the minus 1. So you just expand those out. And then you notice that these two values for the first verification equation are identically equal, so the first verification equation is satisfied. So I'm not going to run through the second verification, checking that is correct, but this is quite a useful exercise to do if you're sort of still getting familiar to these things. Question, probably not to the audience because you can't answer, but to the panelists. Should I leave a little bit of time for people to just run through this?
I think so. You can pause for a couple minutes here.
Pause for a minute or two.
We could take an intermediate question for clarifying on this. Jun asks, how can you be sure that x to the negative 1 exists?
We're working in prime ordered fields is why. So actually every element in your field has an inverse. This wouldn't be true for all fields, but the fields which we're building our groups over, it is true.
Does it need to be non-zero elements for that, everything except 0?
Oh yeah, you're not allowed 0, but the chances of you outputting 0 from the hash is negligible anyway. Mm-hmm. In fact, you'd be quite concerned if your hash output 0. That would probably be a bad hash.
Yes, to clarify, this is a hash function then designed to hash input to a prime field?
Yes. So often how you'd do this is you'd choose something like SHA-256. You'd then hash it in order to get a binary string, and then you'd convert your binary string to a number, and then you'd take that number modulo p.
Ahmed asks, does capital BL leak info about little b1 since
Yes, in
exponentiation?
this example it does. There are ways in order to make it not leak information, but this solution is not zero knowledge.
Got it. I think you mentioned that this is just aiming to be a sound argument, not necessarily ZK.
Yeah.
Well, those are cool questions. Thank you, folks, for asking those. Makes this feel like a real learning session.
Okay, I'm going to move on to the next slide.
Sure.
So the next thing we would need to worry about is that the argument is sound, that a dishonest prover is not able to convince a verifier if the statement they're providing isn't true. So for this, we don't actually need to worry about what our prover looks like. I mean, I can go back and you can see the prover again, but the prover is malicious here, so we can't make any assumptions on what they're doing when we're trying to demonstrate soundness. All we know is that the verifier, no matter what, is going to check these equations and is going to reject if it's not satisfied and accept if it is. So in order to demonstrate soundness, we're going to first look at the first verification equation and try and see what that tells us about the prover's second message, BF, the final B value. So for reasons to do with rewinding that I'm not going to go into, but which largely go from the fact that if you have like one solution to your discrete logarithm problem and a second solution, then they must be equal. If the prover is able to provide some B final such that at random x, BL to the x times B times BR to the power of x to the minus 1 is equal to g1, g2 to the power of x, or to the power of bf, then this implies there exists 6 values, beta 1 through beta 6, such that BL can be represented in terms of the g1, g2 basis, so g1 to the power of beta 1, g2 to the power of beta 2. B is equal to g1 to the power of beta 3, g2 to the power of beta 4, and BR is equal to g1 to the power of beta 5, g2 to the power of beta 6. Okay, so we know that the prover must know some values beta 1 through beta 6 such that this is true. We don't know that they're correct yet. We don't know that they satisfy the inner product argument that we want them to, but we know that there is something. So what we're going to do first is we're going to rewrite the verifier's first equation in terms of these values that we know the prover knows, the betas. So first we have that beta L is represented in terms of g1 to the beta 1, g2 to the beta 2. We know that the verifier is going to take BL to the power of x. So what we're then going to have is we're going to have a g1 to the power of beta 1x term and a g2 to the power of beta 2x term. Similarly, for the B, there's no exponentiation by x here. So here we're just going to have a g1 to the power of beta 3 term and a g2 to the power of beta 4 term. With BR to the power of x to the minus 1. Now we're going to have g1 to the power of beta 5 to the x to the minus 1. That's going to be our first term. And for our second term, we have g2 to the power of beta 6 x to the minus 1. And from the right-hand side of the verifier's equation, we know that this must be equal to g1 to the power of beta f, g2 to the power of x, bf. Now we use the discrete log assumption. So it's possible that a cheating prover might provide some beta 1 x plus beta 3 plus beta 5x to the minus 1, which is not equal to bf. But if they do, then this means that they know some kind of discrete log relation between G1 and G2, which we're assuming that isn't possible. So assuming that's not possible, we have that these two values in the exponent must be exactly equal. Oh, random X going on there, ignore the X. But we do have that the same also applies to the terms involved in G2. So we have that the exponent beta 2x plus beta 4 plus beta 6x to the minus 1 must be equal to bf times x. And if we just do a little rearranging here, take the x to the other side of the equation, we can have both of our equations given in terms of bf. So beta 2 plus beta 4x to the minus 1 plus beta 6x to the minus 2 is equal to bf. Since these two values are equal, we have that the left-hand side of our first equation must be equal to the left-hand side of our second equation, namely that beta 1x plus beta 3 plus beta 5x to the minus 1 has to be equal to beta 2 plus beta 4x to the minus 1 plus beta 6x to the minus 2. Now we have that these betas, which are determining BL, B, BR, were chosen before the prover knew what X was. Because the prover has to choose BL, B, and BR in order to hash those elements in order to find X. And because our hash is a random oracle model, this this means that they cannot later go and change BL once they know X. So if we then have that this equation is always satisfied for any value of X, that means that we have to have that each of our terms in X is going to be exactly equal to 0. So beta 1 is, 0 X term, so X to the power of 1, only appears in our equation once, namely for the beta 1 term. So what this gives us is that beta 1 has to be equal to 0. If we look at x to the power of 0, then we have two terms. We have beta 3 and we have beta 2. So these two terms must be exactly equal. If we look at our x to the minus 1 term, then this gives us that beta 4 has to be exactly equal to beta 5. And if we look at our final term, x to the power of minus 2, this gives us that beta 6 must be equal to 0. So now we have that BF is equal to beta 1 plus beta 3 plus beta 5 x to the minus 1. We know that beta 1 is equal to 0, and we know that beta 5 is equal to beta 4. So if you put them together, we have an exact equation for BF in terms of B3 and B4, which, beta 3 and beta 4, which were our discrete logarithms for our B value, our public input B. And this was what we were trying to achieve with this verification equation. We were trying to say that we know some formula for BF that depends on the form of B. So again, I'm out of a bit of space, so I'm going to take the information which we need from this slide in order to continue, but most of it is about to disappear. So I have an equation for B. I've now renamed my beta 3 and beta 4 by B1 and B3, apparently. That should probably be a B2, just because it looks a little bit cleaner. So now that we have a constraint on what our second message BF is going to equal, we're now going to look at our second verification equation in the C terms. So here we have that CL to the x, CR to the x minus 1 is equal to A1, A2 to the x, all to the power of BF. And we're going to rewrite our verifiers equation in terms of A's and B's. So you have A1, A2 to the x to the power of BF, that's just what your verification equation on the right-hand side says. You know that BF is equal to B1 plus B2 x to the minus 1. So you can substitute that onto the A quite quickly. Oh, I even sort of have on the next slide some boxes so that you can look at just the A1 terms first and see that this is there's no funny business going on. On the second side, I've for the right-hand side of this equation, the A1, B2, x to the minus 1, all in brackets, and then the next bracket, A1 to the B1, A2 to the B2, and then the next bracket, A2 to the B1, all to the power of x. What I'm doing here is I'm separating terms of x. So I'm trying to get the x to the minus 1 terms all together, x to the power of 0 terms all together, and the x terms all together. Again, you can see A1 is looking like it should. Likewise, A2 x to the BF, you know that BF is equal to B1 plus B2 x to the minus 1. A2 is taken to the power of x, so you need to multiply all of that by x. And what you get is A2 to the B2 and also A2 to the B1 times x. So now, again, using the fact that x is randomly sampled, if you have that A1 to the B2 x to the minus 1 times A1 to the B1, A2 to the B2 times A2 to the B1 all to the power of x is equal to CL to the x, C, CR to the x to the minus 1, then what this gives you is that CL must be exactly equal to A2 to the B1. C must be exactly equal to A1 to the B1, A2 to the B2. And CR must be exactly equal to A1 to the B2. And this is what we were trying to prove. We have that B is equal to B1, G to the B1 to the B1, G2 to the B2. And we have that C is equal to A1 to the B1, A2 to the B2. Remember our problem statement here. Therefore, our prover is not going to be able to cheat this without breaking some of our assumptions, either our discrete log assumption or our random oracle assumption. And this is what we need for soundness. So here's a slightly related example. I'm probably not going to give you time to do this now because it would take a little bit of time if you want to go away and give it a go. So here we're going to be trying to, this is actually basically the inner product argument of Bootle et al. In 2016. And they're saying that A is equal to G1 to the A1, G2 to the A2. B is equal to G1 to the B1, G2 to the B2. C is equal to A1, B1 plus A2, B2. Prove that this is true. So we did a paper also on inner product arguments. We were focusing on pairing groups. And in it, we found sort of quite a lot of applications where you would actually use this, this stuff in practice. So to give you all a bit of a break and also to sort of brag about my paper, I'm going to talk about this for 5 minutes or so. You'll observe that the proof that we've done before is quite repetitive in nature. I mean, this is the first time you've seen it, so maybe you won't observe that it's repetitive yet, but every inner product argument you see will be using these same tricks, the same structure. So what you have here is that you can generalize it. You can generalize it such that it applies to any, what we've called doubly homomorphic commitment scheme. So something where you have a homomorphism in the group and also a homomorphism in the commitment key. So by proving this, I don't think that our techniques were especially novel here. But what we do is that we make it really, really easy for anyone else to prove any other inner product argument of this kind of nature. All you need to do is reference our theorem 5.4 and prove that your homomorphic commitment scheme is binding. That will be your proof done, rather than pages and pages of stuff. Application-wise, we came up with 3 major applications. One being a polynomial commitment scheme, and these are very useful for building zero-knowledge arguments. especially zero knowledge arguments that have universal reference strings, so reference strings with trusted setups that apply to any application. We also discuss how you can use it to build a snark aggregator. So if you have lots of Grok16 proofs, then you can aggregate those all up into a single proof and check that. And we also discuss how it can be used such that if you want to outsource a pairing computation, maybe quite a large pairing computation, and check that the result of that is correct, then this is something that you can do. And what's quite nice about it is that the prover, the person saying, yes, this pairing computation is correct, is very, very fast. So rolling up snarks is something that people have been trying to do in recent years. The idea here is being that if you have some application that already uses snarks and you want to make that faster for people to verify, then you're not going to be able to do a snark on a statement about a group. You're going to have to do a snark about a snark. And this is something which is very doable. Typically what people use is curve cycles. So they find some kind of group where you can efficiently represent the group which you proved the snark in, and then using that, they're able to build a snark in the second group about the snark in the first group. The problem with doing this, and it's not like an insurmountable problem, it's certainly the best solution in some situations, but you do have to represent the snark verifier using R1CS constraints. And this can result in quite significant overhead for the prover. So we're talking at least 10,000. Actually, it's probably quite a lot more than that because I'm thinking 10,000 constraints, but then you have to take each of your constraint and take them to an exponential of a group element. So your prover is going to get quite heavy. If you instead use an inner product argument, what you're going to get is that your proof sizes are going to be a bit larger, your verification time is going to be a bit heavier, but your prover is going to be only 6 times faster than running the computation itself. With trusted set.
Slower? Do you mean 6 times slower?
6 times slower, yes I do. Okay. Yeah, 6 times faster would be very impressive. So with a trusted setup, we're able to get the verification down to logarithmic. Without a trusted setup, we can still save on verifier time, but it's not quite so impressive. And we're not able to do anything with random oracle model snarks. We're only really able to do this trick with things like Grok16. The other downside is that we are using our proof elements in the target group. So if you were trying to do this over Ethereum, you'd probably have a problem at the moment in terms of gas costs. If we could get a precompile for the target group operations, then this problem would essentially go away. But at the moment, you would run into this problem, I suspect. The other nice thing that we get, and this is for the polynomial commitment scheme, typically if you have a snark that you're trying to make universal, you're going to end up with a pretty large trusted setup. So recently Aztec ran one for the KCG polynomial commitment scheme, and they had a very large problem that they were trying to prove. And what this resulted in was that the actual setup itself consisted of many, many gigabytes worth of actual data, which then had to be communicated across the network. So the only people that could really participate in this trusted setup ceremony were people that had access to very good internet connections and very good computers. If you were instead to use our polynomial commitment scheme, what you would get is that the setup size would be smaller, and also that the prover time would be smaller. So our polynomial commitment scheme has a square root setup size. So in practical terms, this would take a 32 megabyte setup down to a 50 kilobyte setup is pretty significant. Again, not without downsides. Our proof size is going to be larger. Our proof of time is smaller, which is actually quite a nice benefit. We're able to open polynomial commitments in square root time. But our verifier time is going to be larger, and it's also going to be working over target group elements, which is going to add something, not like an unreasonable amount, but certainly if you compare it to verifying a Grot16 snark, we're not going to come across too well. We can also support bivariate polynomials, and our efficiency depends on the total number of coefficients in the situation of bivariate polynomials. Okay, back to the technical stuff. Before I was talking about a multi-exponentiation argument that was two-dimensional. Now we're going to move to the four-dimensional case. So this time, rather than A1, A2, we have A1, A2, A3, A4. And we're trying to prove knowledge of B1, B2, B3, B4, such that B is equal to G1 to the B1, G2 to the B2, G3 to the B3, G4 to the B4, where G1, G2, G3, G4 are all independent generators. And C is equal to A1 to the B1, A2 to the B2, A3 to the B3, A4 to the B4. So now we're going to run in 5 rounds. Before we were 3, now we're 5. The proof is going to compute a first message, hash it, get some randomness, compute a second message, hash it, get some randomness, and then at the end it's going to output 3 messages, M1, M2, M3. Similarly for the verifier, they're going to take in 3 messages, they're going to send 1 message to the hash function, get back some randomness, second message to the hash function, gets back some randomness, and then given M1, X1, M2, X2, M3, they're going to decide whether or not they think the argument is valid. Okay, I realize there's quite a lot of text on this slide. This is what your prover and verifier would actually look like. Oh, can I break this down? I'm going to talk through it. Your BL and BR terms, you're going to notice, are going to look very similar to how they did in the two-dimensional case. So here, rather than B2 to the power of G1, B2 to the power, G2 to the power of B1, we're going to have our last 2 generators, G3 and G4, to the power of our first 2 exponents, B1 and B2. Now for the BR, we're going to do the same idea, but opposite. We're going to take our first 2 generators, G1, G2, and take them to the power of our last 2 exponents, B3 and B4. CL is going to be similar, but with the A terms, our last 2 A components, A3, A4, and our first 2 exponents, B1 and B2. And CR is going to be equal to our first 2 group elements, A1, A2, to the power of our last 2 exponents, B3, B4. Then given BL, BR, CL, CR, we're going to hash all of those in order to get some randomness X, which cannot depend on BL, BR, CL, CR. We're then going to set some values according to X, A1 to A4, BLB and BR, CLC and CR, and our generators and our exponents. So our first one, A1 dash, is going to be equal to A1, A3 to the X. A2 dash is going to be equal to A2, A4 to the X. And you'll notice a similar pattern going on with our G1 dash and G2 dash. And our exponent B1 B1 dash is going to be equal to B1 plus B3 x to the minus 1. B2 dash is going to be equal to B2 plus B4 x to the minus 1. And then given our changed values, the prover is going to run our two-dimensional multi-exponentiation argument on these rescaled values. And the idea is going to be that if the prover has behaved honestly, then these rescaled values are going to exactly output a two-dimensional multi-exponentiation problem. But if the prover has cheated in any way, and this isn't actually true, then there's no way in which the prover's outputs could actually satisfy the two-dimensional multi-exponentiation problem, and therefore the verifier will be able to catch them out as having cheated. So the verifier is going to compute X with the random oracle given BL, BRC, LCR, and it's going to rescale its public values. So recall that A1 to A4 are all public. BL, B, BR, these are proof elements. CL, C, CR, those are proof elements, and our generators are all public elements. But the private elements, because it doesn't have access to it, it's going to, well, we're going to show that the prover must have rescaled those correctly, but the verifier doesn't need to do any work relating to those. And then the verifier will check their proof with respect to these rescaled elements, which is going to compute for itself. It doesn't just take the prover's word that those elements have been rescaled correctly. Yeah, I think I will set aside 5 minutes here for you to have a go at demonstrating correctness, that this should actually be true. So what you're going to need to do here is you're going to need to prove that B dash is genuinely equal to G1 dash to the power of B1 dash, G2 dash to the power of B2 dash, and that C dash is genuinely equal to A1 dash to the power of B1 dash, A2 dash to the power of B2 dash. And if anyone has any questions, this would be quite a good time to ask.
Okay, we'll pause a little bit for you all to come up with detailed technical questions, work on the exercise, and I'll relay, I guess, only one more question that showed up on the chat in the meantime. I guess it applies to all of these, not just this particular one, but can you say anything about the malleability of these?
So in terms of malleability properties that have actually been proven, no, people haven't talked about this. In terms of intuition as to what I think is going on, it's a random oracle model. Trying to do malleability attacks in the random oracle model is really hard because your random oracle model is spitting out randomness the whole time. So the chances of there actually being an attack there is very, very small.
So malleability attack would be someone takes like those BL, BR, CL, CR, like parts having to do with the statement and changes them in some way, but I guess that like hash.
But if it changes them, then the hash will output something different. So you'll no longer get something that verifies. If you're not careful to hash everything that's important, like for example, here I've described hashing just a proof, but actually you'd usually hash both the instance and the proof, then malleability attacks might come in. But as long as you hash all the important information, you should usually be fine. With a good hash function, you can't be using Pedersen hashes here. You do need to be using SHA or what's the other ones you can use?
So you should at least also hash A1 to A4, is that right?
Yes, yes, you should if you were to use this in practice.
Hi, Mary.
That's assuming that the parameters are fixed, I guess.
Yeah, were you going to ask something?
Yeah, I had one more question. Is there any better way to think about the construction of these proofs than going into the exponentiations? Like, is there a better layer of abstraction in which we can construct these proofs and verify that the correctness and the soundness holds instead of going into the details of how the exponentiations are working and everything?
So, if there is one, I don't know of one. I mean, this was sort of the reason why I was thinking it was quite helpful to run through what's going on here. I mean, you can abstract it in the terms of you can generalize. You can say this maths always works for these type of objects. But I genuinely sort of, from a personal point of view, there might be people that disagree with me here, think that the easiest way to get a grasp of it and to understand it is to just take a small example, no more than sort of 4-dimensional run through it and sort of check that it works. Check why it works. And then when people sort of say, and now we can recurse, you can sort of see how you recurse from the 4 case to the 2 case. And given that it works for the 4 case to the 2 case, you could see why it might work for the 8 case to the 4 case. And given why it works for the 8 case to the 4 case, you can see why it would work for the 16 to the 8 case. And I think this gives a sort of fairly nice understanding for what's going on. So yeah, that would generally be my advice. Just keep it small when you're running through the maths and then scale up when you're arguing for general purposes.
Right. Yeah. Yeah. Thanks.
Sorry, that probably wasn't the answer you wanted.
Yeah, I was thinking maybe like think of these powers like the A's and the B's and as some sort of commitments, and then don't worry about what exact commitment scheme are we using, just abstract them as.
Yes,
Yeah.
that you can do. That you can definitely do.
Right.
Really, as long as you have something which is homomorphic in the group, so sorry, in the commitment key. So in our case, this would be G1, G2, G3, G4. That's a group that's homomorphic, as well as homomorphic in the secret. So in our case, this is the field where we're getting our B1, B2, B3, B4 elements. That's just a field that's also homomorphic. As long as those 2 things are both homomorphic, you can have a generalized argument that should work for anything.
Right.
So I don't see any more questions queued up that are about this slide or immediate preceding ones. There are at least a couple broad questions. So yes,
Okay.
Mary, if you want to go a little further before having the floodgate of questions.
Yeah, I'll continue on, hopefully. I have no idea whether people have had enough time or not. Sorry if you haven't. Okay, so the next thing that, is to show that a prover cannot cheat. And the way we're going to do this is going to look very similar to the way that we did it in the 2-dimensional case. Really, the only thing that's a little bit different is how we start. And how we start is we say, well, we have a proof that the 2-dimensional case is satisfied. So we know that BL to the x, BR to the x minus 1 is equal to G1, G3 to the x, B1 dash for some B1 dash, that must be true. And likewise with the G2, G4 to the x, B2 dash. And given that this is true, there must exist some representation, some beta 1 through beta 12, such that we can represent BL, B, and BR with respect to our generators G1 through G4. Okay, so just sort of taking away the relevant information there. We're now going to rewrite our verifiers equations in terms of betas. So first you have BL to the x. You look at your BL and you sort of take the term for the first generator, put that in, take the term for the second generator, put that in, take the term for the third generator, put that in, take the term for the fourth generator, put that in. Then you do the same with B. Then you do the same with BR. And you know that these are going to be equal to the right-hand side of your, well, this isn't so much a verifier's equation so much as something the verifier has reduced from the recursion, deduced. But we know that this is going to be equal to G1 to the beta 1, G2 to the beta 2, G3 to the beta 1x, G4 to the beta 2x for some B1 dash, B2 dash. Now, because we have the discrete log assumption and we have 2 different representations for some group element with respect to the same generator, we know that those 2 things must be identically equal. So in particular, just looking at the first generator, we know that beta 1x plus beta 5 plus beta 9x minus 1 must be equal to B1 dash. Similarly, looking at the third generator here, and the reason I'm looking at the third generator is because I'm wanting to separate off this B1 dash term, and that's where the B1 dash term appears on the right-hand side. Now we have beta 3x plus beta 7 plus beta 11x to the minus 1 is equal to B1 dash x, which if you take x to the other side, you get a nice equation just in terms of B1 dash. So you have that the right-hand side of your first equation is equal to the right-hand side of your second equation. So the left-hand side of the two equations must be identically equal. And your B1 through B12 were chosen before the prover could possibly have known any information about X. And what this means is that you can put actual constraints on what beta 1 through beta 11 must equal. So X appears on its own, beta 1 is 0. Beta 5 and beta 3 appear, those must be equal with X to the 0. X to the minus 1, we get beta 9 equals beta 7. And our last one, X to the minus 2, gives us that beta 11 must be equal to 0. So if you then plug this back into your equation, beta 1x plus beta 5 plus beta 9x to the minus 1 is equal to B1 dash. And you now know that beta 1 is equal to beta 1 is equal to 0, and that beta 9 is equal to beta 7. This gives you an exact equation for B1 dash. Watch your space, I'm about to delete a load of information, but keep the relevant stuff. So what I'm doing here is I'm just keeping that B1 is equal to beta 5 plus beta 7x to the minus 1. And we still haven't argued about B2 dash. We're now going to do that. It's going to look exactly the same, but for the remaining elements in our verifier equation. We have a discrete log equation. That's going to give us that beta 2x plus beta 6 plus beta 10x to the minus 1 is equal to B2 dash. Similarly, with our G4 generator, beta 4x plus beta 8 plus beta 12x to the minus 1 is equal to B2 dash x, which gives us an equation for B2. Left-hand side of the first is equal to left-hand side of the second. And then beta 2 equals 0, beta 6 equals beta 4, beta 10 equals beta 8, and beta 12 equals 0. So B2 must be equal to B6 plus beta 6 plus beta 8x to the minus 1. Ran out of space again, but just going to put these two equations for B1 and B2 up in the information that we need to keep. And abuse notation and change all of our betas into B1s to B4s. We now look at our second verifiers equation. This time that we have a proof that this verifiers equation must be satisfied. So this time we're going to use that CL to the x times C times CR x to the minus 1 is equal to A1, A3 to the x to the power of B1 dash, A2, A4 to the x to the power of B2 dash. We rewrite the verifiers equation in terms of the A's and the B's. So again, to see that this is done correctly, if we just look at our A1 terms, where we have A1 to the power of B1 dash, we have an exact equation for B1 dash, so we just sub that in. We have an exact equation for B2 dash, so we just sub that in for A2. For A3, this now is A3 to the x to the power of B1 dash, so we just have to multiply our equation for B1 dash by x. And similarly for A4, we have to multiply our equation for B2 dash by x. And that gives us our equation. If we then do some rearranging, all I've done here is taken the x from the brackets out of the brackets. No magic there. But in this term, there's some rearranging happening. all of the powers of x are being put together, all of the powers of x to the 0 are being put together, and all of the powers of x to the -1 are being put together. So now we have that CL to the x, CR x to the -1 is equal to this equation in A1 to A4. Just looking at the powers involving x, we get that CL to the x must be equal to A3 to the B1, A4 to the B2 to the power of x. So CL must be equal to A3 to the B1, A4 to the B2. Look at the powers of x to the 0. We get that C must be equal to A1 to the B1, A2 to the B2, A3 to the B3, A4 to the B4. Looking at powers of x to the -1, we get that CR must be equal to A1 to the B3, A2 to the B4. And this is exactly what we were trying to show. We were trying to show that if the prover convinces a verifier, then they must know B1 through B4, such that B equals G1 to the B1, G2 to the B2, G3 to the B3, B4 to the B4, and C equals A1 to the B1, A2 to the B2, A3 to the B3, A4 to the B4. Therefore, soundness has been showed. So this is my second to last slide. So I'm going to finish dead on time probably. What you'll notice here, a sort of style with what we were going with, is we were trying to do one layer of recursion. We were trying to say, if we have a two-dimensional multi-exponentiation problem, then from that I can construct a solution to a four-dimensional multi-exponentiation problem. And you can do this again. You can double it again using exactly the same tricks in order to get up to an 8-dimensional problem. And because we're doubling each time the number of dimensions that we're working with, what you're going to end up with is a logarithmic sized proof. So just to conclude what we have shown how to prove an inner product argument with 2 dimensions sound. We have then shown how to prove an inner product argument with 4 dimensions sound, given an inner product argument with 2 dimensions that is sound. And what I'm going to sort of say finally is that if you continue in this fashion, you can obtain logarithmic proof sizes for many different types of inner product arguments, but certainly multi-exponentiation problems. Cool. Thank you very much.
Awesome, thank you. I think we have time for a couple of questions. We can go over, have permission from the next speaker to go over by just a few minutes for this one.
Oh, sorry.
One question that you chose, you teased aggregatability for Groth16 proofs.
Yes.
And Shravan asked a question, can you give a little more detail about how that works? I was also wondering about that.
Okay, so Groth16, you have a pairing equation. There's no interaction going on, there's no random oracles going on. All you have is 3 group elements that you're trying to prove satisfy some pairing equation. So what this means you can do is we have a pairing based commitment which allows you to commit to group elements. So you can commit to all of your first group elements into one commitment. You can commit to all of your second proof elements into a second commitment, and you can commit to all of your third proof elements into a third commitment. And then you can run an inner product argument with respect to those elements and some randomized version of the verifiers equation. You do need to randomize because otherwise what happens is you might have that one of your proofs is cancelling out one of your other proofs, neither of which actually verified the first time. But if you randomize the public input to the Groth16 verifier equations, and you make that randomness very very structured in nature, so one will be x, the next will be x squared, the next will be x cubed, etc., then you can make it so that the prover couldn't possibly have come up with any set of proof elements which satisfy the verifiers equations unless their original commitments were actually sound.
Is the main benefit just that the proof size gets smaller, or is the verification?
It's not about proof size or verifier time at all, it's about prover time.
About prover
so,
time.
Because all we're doing in these inner product arguments is the same operation as what you would be doing in order to compute the commitment, which in this case would be pairings.
So you only do one pairing.
You end up with some.
You aggregate.
Not one pairing, logarithmic.
Okay.
No. So what we actually do in the thing is basically exchange pairings for group exponentiations. But then if you have quite a lot of structure in the group exponentiations you're doing, you can then use a pairing on those in order to get something which is, well, actually that part of the proof would be constant size to verify, but you do have a logarithmic cost to verify that the inner product argument is correct. But because you're only doing pairing operations which are algebraic in nature, the prover is going to need to do, I think we calculated it to be exactly 6 times the number of pairings which they would have to do if they were just computing the pairings. So they're not having to take a set of pairing equations, figure out what they look like in terms of R1 CS constraints, represent the R1 CS constraints in terms of group generators, and then compute this huge multi-exponentiation. All they're doing is saying, here's a load of pairings, I'm going to compute another load of pairings in order to convince you that this is correct. So what you end up with is larger proof sizes and larger verification costs, but much, much smaller prover costs.
Got it, thank you. Okay, I don't see any other questions that are snuck in, so I think we can, I'll clap at our laptops for Mary one more time.